Hi everyone, my name is Juliana and I will present our solutions to the challenge together with my partner Alan. We represent our team called GP OSSC, which is composed of 8 members from different areas. We decided to investigate the following research question. What is the best segmentation results that can be obtained employing only the given dataset as a training input? For this motivation, we start the following objects. We have developed a set of methods of this dataset, in particular multi-resolution and successive training. Test new and test of the art multi-resolution methods of this dataset. In order to define weights to the different classes, we decide to apply weights to the classes according to the distribution in the dataset. As a reference, we use the class distribution graph provided in the challenge website. So in the first strategy, we will apply the semantic segmentation approach to the UNet architecture, which opens on-cycle policy. We can see from the graph about the on-cycle policy where the learning rate progressively increase and the decrease moment until they reach a threshold. So in the opposite, we can see the continuing decrease learning rate and keeping moment at the max threshold. And in this figure, we have a multiply training with crescent resolution strategy. So we're also training 2 stages of each resolution, each a transfer learning and a fine-tuning learning cycle each time. In UNet experiment, use the specific classification models with different backbones. The ResNet 34 had the best results, but we can see the validation and test results in the table, and the results are not so good. So we researched the best network for the imaging segmentation, and we found the great results with the high resolution neural network. So we decided to try this model. We chose this model for a second approach. The high resolution neural networks takes a simultaneous multi-resolution learning approach. This model is enabled for easy change to the architecture, adapting a specific task such as image classification, object detection, and semantic segmentation. And we use this semantic segmentation in this experiment.
For the second strategy, we used the original implementation of HR network. The second was implemented in PyTorch and we used the IADOM optimizer. But the one-cycle policy was not used in this experiment. We tested HR in model 18, 32, and 48. Since this model is supposed to learn multi-resolution representation of the images, we trained it using the original network with the original image of the dataset. In the second experiment with this network, we employed the refined implementation of a high-resolution network, which was developed using the FAST AI library. We used the same model size as before, and we imaged with the same as the original resolution. In this experiment, we used the one-cycle policy, like we used in UNet. Here, we represent the results of the previous tested methods. We can see that the high-resolution network showed a great increase in IOU over UNet. And the applied techniques increase the performance even more, like using some of the validation images with the worst IO in the training stage. For all models, a very fast overfitting behavior during training could be observed, as amplifying the training curve of HR18 model in the figure. The observed fast overfitting behavior could be justified by many factors, like the small size of the dataset allied to the complexity of the data. Some underrepresented classes like SEN have never obtained good results. Another problem was the number of vegetation classes. This caused the segmentation leakage between vegetation classes, leading to low IO for these classes. This figure shows some examples obtained with HR and UNet. The good results are below, and the bad are. We chose these results using visual inspection, né? Daí, pode passar. In this figure, we show some of examples of leakage on results obtained in strategy tree. Merging the vegetation class into navigable and non-navigable paths could solve this problem. The results shown in this table were obtained in a Jetson TX2 in the RTK dataset. We convert the PyTorch weights to O9X and use the TensorRT to further optimize the models. We were able to run the high-resolution network at 21 FPS, with a little loss in accuracy. And the HR model is way faster than UNet model. And those results show that this network, in the form of the refined version, have potential to be a very good choice for embedded navigable paths detection, and deserve further study and refinement. I'd like to thank you for the attention, and we will be happy to answer any question you may have.
Thank you, Juliana and Alan, for the very interesting presentation. Are there any questions coming in from participants raising their hands or in the chat? Maybe in the meantime, while we're waiting for them, could you maybe explain a bit more what the one cycle policy is, just in case not everyone knows what that does?
The one cycle policy, it's not not very known. It is a strategy for training neural networks where you vary two important hyperparameters, the learning rate and the momentum of the network during a full training cycle. And whilst you increase the learning rates, you lower the momentum. And then you converge again to the original values you had in the beginning of the training. This must be defined in the beginning of the training, because once you start it, you can't change these parameters anymore. You can't simply stop a network and then start training again. It won't work. This is the only difficult part. So this strategy is in a paper by Leslie Smith, and I see it only implemented in the FastAI framework, which is a high-level framework built upon PyTorch. And we found this implementation of the AirNet on FastAI. We made a few modifications and you can use it. So when you use the one cycle policy, you can see a tremendous increase in learning speed. It's really interesting. If you test it on HRNets, for example, for image classification, you see the difference between training and HRNet, some standard implementation in PyTorch, and training the same network in its implementation in FastAI. But the only difference in hyperparameters being the one cycle policy. So we were searching for an implementation of the HRNet, which we think is a very interesting model. And I see it here. Many of the other works tested HRNets. I think it's very different from all other approaches we had up to now, because the HRNets have a model that is homogeneous. It's mathematically elegant. It's very different, for example, from a detectron, where you see a lot of different things patched together. On the HRNet, you have a multi-resolution approach, homogeneously treated in one model. So we tried to find an implementation of the HRNet which was using the one cycle policy, and when we find it, we corrected a bit of the software and we tried it, and you see the difference. It trained faster, it's almost twice as fast as the normal HRNet, and the results are much better. So that's a very short description of this. For who is interested in the one cycle policy, we have all the references in our paper. So you can find it there and eventually implement in your own neural network if you use a TensorFlow or other API for your networks.
Thank you for the very interesting comment, Aldo. So that it's quite a pity or too bad that this one cycle policy is only implemented in a FastAI framework so far, but that is something that can be changed. The it was a good segment to also mention that all participants, or like the all top 3 performers, also wrote a technical report, which will be uploaded onto the workshop website in the next week. We're still gonna review and give some feedback on the reports so far, but they're looking pretty good.